get into this next session. So we have two more talks in this session, and the first one is by Diego García-Martín, who's going to tell us about the theory of overparametrization in quantum neural networks. So please go ahead.
Okay, thank you very much. Can you hear me well? Yeah, okay. So yeah, I'm Diego. First of all, I would like to thank the organizer for giving me the great opportunity of talking at this conference. So today I will talk about the work that was done while I was participating in the quantum computing summer school at Los Alamos National Lab, and which gave rise to a paper that we call Theory of Overparametrization in Quantum Neural Networks. So here's the overview of the talk. So first I will start with a background section where I will introduce the concepts that will be needed to understand the rest of the talk. So first of all, I will briefly review variational quantum algorithms with a particular focus on what are the relevant mathematical space that we should look at when we try to analytically characterize and study this type of algorithms. Then I will introduce the concept of the dynamical Lie algebra, which will be a central concept throughout the talk. And then I will introduce the Fisher information matrices, both classical and quantum, which will also be relevant during the talk. Then I will move on and present the main results we have, analytical, and then I will show some numerical experiments that we did to illustrate these results. And then finally, I will wrap up with some take-home messages. So let's get started. Variational quantum algorithms. So these are a class of quantum algorithms that have become very popular in recent years. And the main reason for this popularity is that there is hope that these algorithms will provide a meaningful quantum advantage for some practically relevant problem on niche devices. So that means with shallow circuits and without error correction. So it is fair to say that this is at the moment quite unclear. But in any case, even if they couldn't provide this advantage for niche devices, I still see a lot of potential for them in fault-tolerant regime. Okay, so what are these algorithms? So they are hybrid algorithms. So we will have a quantum computer and a classical computer working in tandem. So the role of the quantum computer will be to prepare a trial state using a parameterized quantum circuit. So this circuit will have parameterized gates with continuous parameters that we can modify. For instance, you can think of single qubit rotations, where the rotation angle is the variational parameter. Then once we have this trial state prepared on the quantum computer, we will measure some observables, we will collect statistics, and then we will aggregate these results to evaluate a given loss function that we aim to minimize in order to try to solve our problem. And then we will fit this loss function to a classical optimizer, which can be gradient-based or gradient-free or whatever. So this optimizer will provide a new set of parameter values that we will fit into the quantum computer. We will prepare again a trial state, evaluate the loss functions, and then iterate this process trying to minimize the loss function. And by the way, so you might have noticed that I refer to quantum neural networks in the title of the talk, which is just a fancy name. And by that, what I mean is whenever we don't have just a single initial input state, but rather we have like many quantum states as input, like coming from a training set, then this is what I will refer to as a quantum neural network. So now, what are the relevant spaces that we should care about when studying this algorithm? So here, first of all, of course, we have parameter space, right? So if we have m parameters, real parameters, then this space is just Rm. So this is an Euclidean flat space, right? So if I want to go from the yellow point to the green point, then I can know what's this distance from delta theta 1 and delta theta 2 just by applying Pythagoras theorem, right? But then our parameterized quantum circuit will induce a map to unitary space, where here we will have the set of all unitaries that can be implemented by our quantum circuit when varying these parameters and when allowing for sufficient depth. And it turns out that this set of unitaries that our circuit can implement, they form a Lie group, which therefore has an associated Lie algebra, which I will introduce in the next slide. Then we have a third map, which is induced by the action of this unitary group onto the initial states that we have. And this is Hilbert space, or rather like projective Hilbert space, more formally. And so this is just the manifold of states that can be reached by changing the parameters of the circuit and when allowing for sufficient depth on the circuit as well. So clearly these are two different spaces, right? Here we have unitaries, here we have quantum states. And for instance, you can think like when we have like a single input state to the variational circuit, then this map is induced by, for instance, like the all zero states in the computational basis. Then this map is induced by a single column of the unitary, right? So we will only care about one column of this unitary, which gives us the action on the initial state, and the rest we won't care about it. And then finally, we have the loss function landscape that we want to minimize. And here we want to move in this space to try to find a global optimum. And in general, this landscape will be highly non-convex. So in this work, the kind of circuits that we studied are what we call periodic structure ansatces. And what this means is that we will have a basic unit cell or layer that will repeat itself along the circuit. So each layer can have different values for the parameters, but the gates and the qubits on which these gates act are the same on each layer. So our result, so it's a very like pretty general setting, and it is the kind of circuits that most people consider when doing variational quantum algorithms. So if we have these kind of circuits, if we have, let's say, capital L layers, then we can express our unitary as the product of the unitaries for each layer, and then crucially, each layer can be also written as the product of some exponentials, e to the minus I theta lk hk, where hk is a Hermitian operator, right? And the thetas are the variational parameters. So here, since we can always write our layers like this, we refer to these hk's as the generators of our circuit, and this will be an important concept. Now, the dynamical Lie algebra, what's this? So this is the dynamical Lie algebra G is the space spanned by the nested commutators of the set of generators of the circuit. What this means, so imagine we have two generators, a circuit with two generators like here, like H1 and H2, and then we take the commutator between these two. This gives us a new operator, which in general will be linearly independent from the previous one, from the previous two one. So if that's the case, we add it to the list, and then we compute again commutators between all the operators in that list. So I do H1 with commutator H1, H2, and commutator of H2 with H1, H2 again. And I do so until I cannot generate anything that is linearly independent from what I already have. And when this happens, we say that the algebra closes, and all these operators that we have generated by taking nested commutators are the basis of a subspace, which is the dynamical Lie algebra of my circuit. And why do we care about this? Because, and if we take a look at the BCH formula, if we have this product of unitaries generated by Hermitian operators, we can always rewrite this as a new exponential of a new A operator, and this operator can be written as a linear combination of the elements of, in my Lie algebra. And if I now add a new third generator, then again, the new operator that will arise here in the exponent will always be within this Lie algebra. Therefore, we can see that the algebra generates all the, tell us what are the possible unitaries that you can generate from your circuit. So as a simple example, imagine that we have H1 equal to the sigma x Pauli matrix and H2 equal to the sigma y Pauli matrix. Then we take the commutator, sigma set will arise here, and therefore we will have the full algebra, right? We will have all Pauli matrices, and therefore that's why we only need Rx, Ry rotations, for instance, to generate any single qubit unitary. This is a meme by my colleague Marco Cerezo, and it tries to convey the message that indeed Lie algebras are a powerful analytical tool to study variational quantum algorithms, quantum machine learning model. And as an example, I will refer you to this paper where the authors show that you can diagnose whether your variational circuit will have barren plateau or not from the dimension of the dynamical Lie algebra. So if the Lie algebra has a dimension that is exponential in the number of qubits, you will have a barren plateau, whereas if you have a dynamical Lie algebra with a dimension which is at most polynomial in the number of qubits, then you will not. And the last piece of background that we need is the Fisher information matrices. So I'll start with the quantum one. This is an m by m matrix. So if we have m parameters in our circuit, this is an m times m matrix. Therefore, its size is determined by the number of parameters of my circuit, right? So here, this is the definition of the matrix elements. It's not obvious at first sight what this means, but never mind. What we care about is written in this formula here below. So remember these different spaces that we had. So we have parameter space, unitary space, Hilbert space, and loss landscape. So, okay, I know how to compute distances in the Euclidean flat space, right? But it is not obvious like how these distances translate into distances in Hilbert space. So imagine I have a circuit with a control rotation, and imagine that the circuit, the state of the qubit that controls this rotation is on the 0 state. Then I can vary my parameter as much as I want, but I will not move in at all. I will not be moving at all in Hilbert space. So this translation between distances in parameter space and Hilbert space, this is what the quantum Fisher information provides us, right? For a small infinitesimal variation of the parameters. And here I'm just taking this as a distant measure, the infidelity. Similar thing with the classical Fisher information matrix, but now suppose we have a quantum state, we want to extract information from it, therefore we have to measure it, and that will give rise to a probability distribution. So what is the distance between probability distributions when I vary my variational parameters? Well, this is what the classical Fisher information gives us, this translation between parameter space and probability distribution space. Well, here I'm taking as a distance the Kullback-Leibler divergence, but it turns out that contrary to the quantum case, you can take any distant measure as long as as long as it fulfills certain properties like monotonicity and so on, you will end up with the same Fisher information matrix up to constant factors. Okay, now the main results. This is the main result that we have. And it states that the rank of the Fisher information, the quantum Fisher information matrix for any input state to your circuit is upper bounded by the dimension of the Lie algebra. Okay, this is the main thing, so I'll repeat it just in case. So the rank of the quantum Fisher information matrix for any input state to my circuit is upper bounded by the dimension of the Lie algebra. And here I have some numerics for two different types of variational quantum circuits. Doesn't matter with different Lie algebras, it doesn't matter which circuits these are now for the time being, I will tell you later. And here I'm just plotting the spectrum. So in the y-axis, I'm showing the value of the eigenvalue, and on the x-axis, I'm showing just an index label in the eigenvalue. So we can see that there is a clear separation between non-zero and zero eigenvalues, right? And we see that the number of non-zero eigenvalues, that is the rank, is upper bounded by these vertical lines, which are the dimension of the corresponding dynamical Lie algebras. So what this means is that if you are adding layers to your circuit, it comes a point where adding more layers is not increasing the rank of your quantum Fisher information matrix. It's only adding zero eigenvalues, right? And it turns out that, remember that I told you that the quantum Fisher information matrix translates distances between parameter space and Hilbert space. Therefore, the rank of the quantum Fisher information matrix is telling us how many relevant and independent directions we have in Hilbert space at a given point in the landscape. So this means that if you are adding zero eigenvalues, you are not being able to explore any new direction in Hilbert space. This leads us to this definition of overparametrization. And we say that a quantum neural network is overparametrized whenever the rank of the quantum Fisher information matrices for all the quantum states, the input states to my circuits, are saturated, or in other words, they achieve their maximum possible rank. So yeah, as I said, so this means that if all the feature information matrices for my input states have saturated their rank, it means I am exploring all possible directions that my circuit gives access to when changing the parameters and going to sufficient depth. And why may this be beneficial? Well, let's imagine that we have a loss function hypersurface. We take a 2D cut, and let's look at it at along one variational parameter. So in general, if this is not monotonic, this will be non-convex, and it will have some local minima, right, along this direction. But it may happen, it may well happen, it need not happen, but it may happen that if you add another new direction that you can explore, then it can happen that this local minima is no longer a local minima, but it becomes a saddle point from which your optimizer can escape. And of course, so these traps that disappear whenever you add more directions, they are called false traps. And whether these traps will disappear or not will depend in general on your loss function, because here we are just talking about the quantum feature information matrices. This is all at the level of Hilbert space. So I didn't say anything about the loss function. But what I can say is that numerically, what we can see is that for several relevant practical problems, we see that virtually all local minima disappear when we go to the overparametrized regime. This is the second result that we have. And this states that the capacity of a quantum neural network is upper bounded by the dimension of the Lie algebra. It doesn't matter too much now what is the capacity of a neural network. This is just terminology for machine learning audience. But you can think of it intuitively as quantifying the set of functions that it can capture. So okay, see, if we take these two different definitions of capacity, taken from these two references, well, in this first one is trivial to prove this statement. And in this second case, what we need is just to prove that the classical physical information matrix is also upper bounded by the dimension. The rank of the classical physical information matrix is also upper bounded by the dimension of the Lie algebra. And our third analytical result states that if we have a loss function of this form, so we have an input state row, we apply our parameterized unitary, and then we measure some observable, then the rank of the Hessian at the global optimum for this loss function is also upper bounded by the dimension of the Lie algebra. Okay, here there is a technicality if the dimension of the Lie algebra is too large, but it doesn't matter. And here again, you can see the spectrum at the global optimum and at random points. So this means that when I am approaching the global optimum of my loss function in the loss landscape, then I will have at most DMG relevant directions to go to it. With this, I will show some numerical experiments to illustrate the overparametrization phenomenon. So we will consider two different types of variational quantum circuits. First, a Hamiltonian variational ansatz, inspired by the transfer field Ising model. So here we have this set gates with beta parameter. You see it's the same parameter in all of them. So this set gates, this is just e to the I beta sigma set. And then we have a single qubit Rx rotation with the same parameter. And then we will consider both periodic boundary conditions and open boundary conditions. And we can prove that the dimension of the Lie algebra for the open boundaries is quadratic in the system size, and it is linear in system size when we have closed boundaries. So this has this circuit, when okay, this is one layer. When we repeat this, this has a polynomially large Lie algebra. Whereas here we have a hardware efficient ansatz with Ry rotations, Rx rotations, then control sets, again single qubit rotation, then control sets in alternating qubits, and so on. So it turns out that this circuit is very expressive. It can generate any unitary. So it has a dimension, associated dimension of the Lie algebra. It's exponential in the number of qubits. And here, this is the simulator that we use for our simulations. So we use our first circuit the one with the polynomially large Lie algebra to do a variational quantum eigensolver on the transfer field Ising model. So here I'm plotting on the y-axis. This is the difference between the energy obtained by the VQE compared to the exact ground state energy obtained by diagonalization. And here on the x-axis is the number of iterations of my classical optimizer. So in blue, we have like few number of layers, few number of parameters. And as we move towards spread, we are increasing the depth and therefore the number of parameters. So what we can see is a phase transition. If you have like few layers, few number of parameters, you cannot converge to a good minimum. And moreover, when you increase the number of parameters, the increase in accuracy is slow, whereas it comes a point beyond which the convergence becomes very good. It becomes exponential in the number of iterations, and you can reach the global optimum. And I should note that here what I'm plotting, this is the average over, so each line is the average over 50 random initialization, so it's not just our best run. And then the shaded regions are the standard deviation. So what it means, these red curves, it means that every single instance converges in the same way to the minimum. Because if we had like a single outlier, let's say that gets trapped at the minimum at, let's say, 10 to the minus 5, when we average over 50 random instances, the average will be 10 to the minus 6 or something. So here it means that we are systematically reaching the global optimum with exponential convergence, which can only mean that we have a very favorable optimization landscape. Here, to further illustrate this computational phase transition, here what I'm showing is the ratio of instances that converge within an error of 10 to the minus 7 to the global optimum versus the number of parameters in the circuit for different system sizes. And we see that if we have few parameters, none of the instances converge, but then there is a critical point where the landscape starts to change, and then some instances converge, whereas others don't. And if you go past this point, then every instance converges. And as you can see, this critical point is marked by these vertical lines, which indicate the dimension of the Lie algebra of my circuit. So when I have a number of parameters which is around the dimension of the Lie algebra, then I get to the overparameterized regime and I go through this phase transition. And here on the right, I'm showing the rank of the quantum Fisher information matrices and the Hessian for different number of qubits, and yeah, both close and open boundaries. Close and open boundaries, and we see the solid lines are the upper bounds, and we see that the rank is within these bounds. So next problem that we looked at was unitary compilation. So basically, this is we sample unitary from the hard measure, and we try to approximate it with our hardware efficient ansatz. And we see same sort of phase transition, right? And again, same thing here. Yeah, phase transition marked by the dimension of the Lie algebra. But the important thing here is that in this case, we have a circuit that is very expressive. It has a dimension which is exponential in the number of qubits, which means that if we want to go to the overparameterized regime, we need to increase our depth, the number of parameters, exponentially with system size, which means, of course, that this is not scalable. And here we have, again, the ranks, which scale exponentially. So that was it. I'll now repeat the main conclusions. So overparameterization is a phenomenon whereby adding parameters to a variational quantum circuit beyond a critical value results in a much favorable optimization landscape. Here I should say that this had been observed empirically before our work. There are at least a couple of papers. There is one by Seth Lloyd and co-authors in Learning Unitaries by Gradient Descent. There is another by Felipe Carrasquilla and co-authors, also showing overparameterization in VQE tasks. But there was a lack of theoretical understanding of why this was happening. So here we provide some results that help better understand this phenomenon. And we show that the number of parameters at which this computational phase transition can be linked to the rank of the quantum Fisher information matrices across the landscape. And we show that this rank is upper bounded by the dimension of the dynamical algebra obtained from the generators of the circuit. So therefore, if we want to design ansatces with good properties that can be trainable, can be scalable, we certainly want to look at ansatces with at most polynomially large dynamical algebra. And these are good candidates because they can both potentially reach overparametrization with a polynomial effort and also avoid barren plateaus. And with this, I will finish. I will thank my amazing co-authors, Martin Laroca, Nathan Yu, Patrick Coles, Marco Cerezo, and I'll thank you also for your attention.
Thank you very much for that really nice talk. We have time for some questions. Yeah?
Thanks for the talk. I've got a question about the parameters, whether it has an effect whether you have them in parallel to multiple gates in parallel, or if you have like multiple layers.
So maybe I can just repeat this for people on Zoom. The question is, does it make a difference whether the parameters are happening in parallel or sequentially?
Yeah, so it does. So for instance, here you can note that like every single gate has a different parameter. This will increase the dimension of the Lie algebra by a lot. Whereas here we have correlated parameters. This keeps the dimension small. And but it is not guaranteed that just having like these correlated parameters will give you a polynomially large algebra, because so here we have a Hamiltonian variational ansatz from the transfer field Ising model, which has this dimension. But if you go to the both longitudinal and transverse field Ising model, which would just amount to add here a layer of R set rotation with the same parameter, then you change completely the dimension of your circuit, and it becomes exponential.
But if there's no correlation to the parameters, would it be the same value for independent parameters in parallel?
You mean like independent parameters, like in this case where we have, yeah, it definitely can have a big influence. Like if you have like, so for each parameter, so you're having one generator for each parameter, right? So in principle, one should expect that the larger the number of generators, the larger the algebra, but not necessarily. So I mean, answering in full generality, it's not possible, or from what I know, but typically, yeah, adding more generators will typically increase the expressibility of your circuit, the number of generators, and therefore the algebra.
So if there's no more questions, no more questions about it.
So, any other examples? I guess here the sole dimension of the algebra is just 3 fermions or multiplication scarce. So, like, I don't know of any interesting classes of dynamical algebras that polynomial dimension, like local intergroup works.
Yeah, that's a very good question. It's difficult because as long as you stay within 3 fermions, then everything's polynomial and it's nice. But yeah, but if you go to interacting models like the X-set model, then the dimension of the subspace is when the number of magnons grows with the number of qubits, like n-half, let's say, like the ground state subspace, then the dimension is exponential. So as far as I know, for every well, I don't know if every, but for the models that we looked at, when they are interacting, then the dimension of the Lie algebra in many subspaces is exponential.
Yes?
For the classical simulation, what optimizers would be used? What would be like the main obstacles to run it on real hardware instead of on simulator?
So you asked what's what's the optimizer that we use? Yeah, it's a gradient descent, so it's Adam with adaptive moment, and we use this gradient-based method because we wanted to probe the landscape and see whether the minima would disappear. So we thought that the gradient-based was the choice the appropriate choice. So and there was something about implementing it on.
So what would be the main obstacles now rerunning the same experiment with the hardware? Because I guess probably you can't do that well with hardware because that gets the gradient that nicely.
Yeah, well, I don't know, I guess like, yeah, there will be some, I mean, you have to communicate between the quantum processor unit and the classical processor unit where you are running this gradient descent. But I don't see much difference between this communication, whether you have a gradient based or a gradient free. I mean, it may take longer to do a gradient like a genetic algorithm or something, but it's like fundamentally it's the same thing, I would say. But I'm not down to the experiment.
I guess in the interest of time, we should bring things to a close there. So let's thank the speaker again.